In this video, we're going to be talking about inverse variation. So if you haven't watched the direct variation or gotten those notes, make sure you get those first. Everything we learned about direct variation is basically going to be the opposite here in inverse. If you hear like bells or jingles, what is these phrases called? Not that that's important, but that's what that sound is. Anyway. For inverse variation, an inverse variation is a specific relationship in which there is a constant, so just like direct, but with direct variation we had a constant ratio of y over x. With inverse variation we have a constant product where we have y times x between all of the ordered pairs. An inverse variation equations are written in the form y equals k over x. So just as with the direct, the product that we got, or the ratio, with direct it's ratio. The ratio we got that didn't come out of thin air, we got that from the equation. So if we're trying to solve for the constant of proportionality, the k, in our equation right here, we would solve for k by doing one of two things. Either cross-multiplying, so remember that y is really over 1, so I could cross-multiply, so this would be y times x equals k times 1, which would really just be yx equals k, which is how we get this product to find our constant. So now we're going to go through some examples, just like we did for the direct, where we find what this constant is. So if we are finding the constant, remember that to find that, we need to multiply y and x. So we would multiply these two and see what they are. 1 times 20 gives us 20. Make sure that is the constant for all of them, because if it's not, then these aren't an inverse variation. 2 times 10 is 20, 4 times 5 is also 20, so that works. And then we need to write the equation to represent the relationship. So because it needs to be in the form y equals k over x, this would be y equals 20 over x. Now, what I was going to say, we can hold that thought. I'll come back to that. Let's do number 4. Same thing, even though it's in a table, to find our constant k, we would need to multiply x and y. So here for number 4, if we multiply negative 0.5 by negative 12, that's the same thing as saying negative 12 divided by negative 2. So this would give us positive 6. And then we just need to make sure that all of these have the same constant. Really, we multiply negative 1/2 and negative 12. I just, in my head, converted it back to a fraction and multiplied it that way. But when you're multiplying fractions, you're really dividing when you have a whole number in your fraction. For the next one, negative 1 times negative 6 is positive 6. Negative 1.5 times negative 4 is negative 6. Or if you wanted to convert it to a fraction, that would be negative 3 over 2 times negative 4, which would be positive 12 over 2, which still is 6. And then negative 2 times negative 3 is positive 6. So all of those have the same constant, so we can say this is an inverse variation. And then our equation for this one would be y equals 6 over x. Now, the next part of these notes talk about graphing inverse variation, and that's a little bit more advanced than I really want to talk about with you guys. You could definitely look at it, try it. So what it does is it gives you what the constant k would be. So here they say k is 16, so that would tell you your equation is y equals 16 over x. And then you can pick x and y values. So let's say I pick the point 1. If I put 1 in for x, 16 over 1 is 16. If I put 2 in for x, I'm sorry, and I should probably plot that point. 1, 16, okay. If I put 2 in for x, 16 over 2 is 8. So that would be the point. Oh, I forgot. These are counted by 4, 2, 4, 6. Yeah, okay. So this should have been here. 2, 8 would be right here. I'm not going to do 3 because 16, I'm sorry, 3 doesn't go into 16, but I'll do 4. 16 divided by 4 would give me 4. So 4, 4. Okay. 5 would work, 8 would work. 16 divided by 8 would give me 2. So that would be this point right here. And then the last number I could use is 16. 16 divided by 16 is 1. So that would be somewhere here. What you end up with is something that looks like this. However, we also need to put in some negative values here. So let's say I put in -1. I'm really just going to use the same numbers, but make them negative. So 16 divided by -1 would give me -16. -2 would give me -8 if I put that in. -4 will give me -4. -8 would give me -2. And then -16 would give me -1. So then that one would look something like this. This way we have variables on both sides. This is more advanced than I really wanted because 1, we're not graphing these. 2, they're talking about asymptotes, which is something that you will talk about in Algebra 2. I think that's when you talk about it, yeah. And these equations themselves, rational functions, we are not really going to deal with, except I feel like maybe early on we talked about domain and range. But is there, so you see what it looks like, but any inverse variation, we know direct variation is linear, goes to the origin. Any inverse variation kind of looks like this, where it's like curved, and it has arrows really in 4 places, and it's going all over the graph, but not at the same time. That's as much as we're going to do with that. I'm sorry, that's as much as I'm going to do with that because you guys aren't going to do anything with this until you get to like an Algebra 2 class or higher. So moving right along, we are not going to do those. We're going to go to the finding the missing values. This process is very similar to the direct variation process, except we have to remember that y equals kx in this case and not k over x is what I should have said. And not like the direct where it's k times x. As well as to find k, we need to multiply y and x together. So to go through a couple of these examples, we're going to do number 7, or start off with that one. So first, we need to find y, but we also need to determine the constant to kind of help us find what that value is. So if I multiply 12 times 14, that should equal -24 times y. So that would give me 168. And then I could solve this by y, or solve this for y by dividing. Now because y times x is k, my constant should be 168. I'm sorry, my brain. I'm talking and doing math at the same time, and my brain is not working. We need to divide by -24. There we go. to give us -7. So if we were to go back and double check, -7 times -24 should give us the same constant, 168. Which it does. So these didn't say write the equation, but because they have the same constant, this would be an inverse variation, and we could write that y equals 168 over x. Now let's do number 10. Same thing, we can multiply -7 and x. Really, the order doesn't matter here because multiplication is commutative, but in general, we usually put the numbers first, which is why I put it like that instead of, I'm sorry, this case wouldn't have mattered because y is a number, but like in the one we just did where I did -24 times y instead of y times -24, that order does not matter. But back to 10, this should equal -3 times 21, or if you put it the other way, that's fine too. I believe this is 63. Yes, but negative. So we have -7x equals -63. And if we divide both sides by -7, that would give us 9, positive 9, yeah. Since we multiplied -3 and 21 together already, we know that our constant should be -63. And if we multiply 9 and -7 together, we do get -63. So if we're writing our equation for this inverse variation, this would be y equals -63 over x. Let's do a couple more of these and then we'll go on to the application of word problems. Number 11, same thing, but now it's written in words. We now have when y equals 9, x equals -6, find x when y equals 3. So for this, we have 9 times -6 equals x times 3, or 3x if you rewrote it that way. So this would be -54 equals 3x. So -54 would need to be our constant. Divide both sides by 3. I believe that's -18. Yes. So -18 answers the question. And then our equation, so if I multiply -18 and 3, we do get -54, so that would be our constant. So our equation would be y equals -54 over x. And then the last one of these that we're going to do is 14. So for 14, we have y equals -8 when x equals -7. We need to find y when x equals -4. So we set up our equation and then we can solve for y. So this would be positive 56. Yes, there's a lot of hesitation in that because I was like 50 something. But yes, 56, okay. And then we have equals -4. We divide is the word I meant to say there. Divide both sides by -4. We get -14. And then if we go back and we check, -14 times -4 gives us a positive 56. So 56 would be our constant k, and our equation would be y equals 56 over x. Right. Hopefully you see the difference in how we solve and find missing values for direct and inverse variations. Now let's actually do some word problems. Just as with any word problem, read through it, find anything you find that is important. So number 7, we'll read through, and then we'll highlight, then we'll set it up and solve. Time traveling varies inversely with average speed if a train travels between two cities in 3 hours at an average speed of 65 miles per hour. How long would it take at an average speed of 78 miles per hour? So we know that this is an inverse variation, like I said before in the direct variation video. It usually says what it's doing. Varies directly, varies inversely. It'll say something along those lines that you know which one it is. Okay? And then we have our numbers, 3 hours, 65 miles per hour. We know those are important because they say time traveling, so it has to be an amount of time. And then they said average speed, so I should honestly highlight those two. So the 65 miles per hour would be an average speed, and they say that's what it is. Then we're looking for how long would it take. So they give us an average speed, and we have to find the amount of time it would take. So first, we're going to solve a couple of these, like we're using the equations, finding the k, and going through that process. So with these, time traveling varies inversely. Anytime we set this up, immediately be thinking y equals k over x. Or if you change the variables, let's say t and a, for time and average speed. We really should be defining these variables if you change them, if they're not x and y. I don't believe I did that in the direct video, but we should be doing that. Okay, so time traveling varies inversely with average speed. That means A is going to be underneath K. Then they tell us the train travels 3 hours at an average speed of 65. So with this, if we're solving for K, we would multiply both sides by 65. Remember that this is kind of the same thing as cross multiplying because there's 3 over 1. So you'd have 195 equals K. So that would be our constant. If you wanted to rewrite your equation, T equals 195 over A. We are looking for the time when our average speed is now 78. So we put 195 over 78, and our answer here would be 2.5, and in this case, I would assume it's hours, per hour, yeah. Make sure that you put your units, since this is an application word problem. For number 8, I'm going to read it and highlight as I'm reading. The company that produces laptops has determined that the number of laptops it can sell varies inversely. Wow, I deleted my highlight. Varies inversely to the price of that laptop. Then it tells us 2,000 laptops can be sold when the price is $2,500. So let's set that up. We know it's going to be, if we're using different variables, let's say N for number of laptops and P for price of laptops. Then we can say N equals K over P. They tell us the number of laptops is 2,000. and the price is 2,500. I'll just put them in the wrong spot. It should be K over. So to solve for K, we would multiply 2,000 by 2,500. And we get that K equals 5 million. Then we could use that to find the number of laptops sold if the price is 1,000. So we're looking for a number of laptops. So we're going to put in 5 million over our price, which is 1,000. And we would get 5,000. I'm running out of space. And then our unit would be laptops. 5,000 laptops would be the number they would need to sell if the price is 1,000. Or can be sold if the price is 1,000, I should say. Right. The last one we're going to do is going back to the method we talked about earlier for finding missing variables. So with that method, let me read the problem first. The width of a rectangle varies inversely with its length. So if I were to set that up, well, I'm sorry, I'm going to do this differently. So you could still set it up the same way, W equals K over L and solve for K, and then find the missing pieces. But I'm going to do this a little different. We know the width is 4 when the length is 18. And then we need to find when the length is 8. So taking back what we know already, we know that y equals k over x. We also know that k equals y times x. So here, let's say our width is y and our length is x. That means this is a y, this is an x, this is an x, and we're looking for y. So this would be 4 times 18 equals y times 8, or 8y, either or. I changed this to y and x, but thinking about it, you could have also used w and l, just replace everything with that. So either or, that part doesn't really matter. And then we would solve 4 times 18, we get 72, so that would be our constant, k. Divide both sides by 8, and y would equal 9. This doesn't have like inches, centimeters, anything like that, so we could just say 9 units. So again, if you like that method, you could definitely use that method. Or if you like the other one, you can use that one. If you, for width and length, you don't need to define them because it's width and length. But if you change the variables besides x and y or w and l, like maybe you like your initials, so for me I use T, well I couldn't use that because of the same. What if I do use T and M? I would just need to say what T and M equal. Right? So we have gone through all of the inverse examples that I wanted to go through. You will not have time to practice, whether that's Delta Math Khan Academy or the other practice. Let me know if you have any questions.